Hi everyone, Kevin C. here with another edition of SRJC Wine Studies Online. Today we're looking at standardizing sodium hydroxide. So remember back when we determined titratable acidity, we got the measure of TA because we used sodium hydroxide to neutralize all the acids in the wine. Remember, we had the burette set up, we had sodium hydroxide in the burette, we dripped that into a wine solution until we got to the endpoint of pH 8.2 when phenolphthalein turned pink. And then we determined the amount of sodium hydroxide we used and the concentration of the sodium hydroxide. And based on that, we could determine the amount of acid in the wine. So sodium hydroxide neutralized the acid. Based on the amount of sodium hydroxide used, we could tell how many acidic protons were in the wine. That whole calculation is dependent on an accurate concentration of sodium hydroxide. One of the things wineries don't often do is standardize their solutions of sodium hydroxide. And the reason it's an issue is this. Carbon dioxide in the air will dissolve in any solution. So when CO2 comes along and it dissolves in our solution of sodium hydroxide, the CO2 will react with water in that solution to form carbonic acid, H2CO3. Well, now we have an acid. Before, we didn't have an acid. We had CO2 and H2O. H2O could be considered a very weak acid. But now we have a stronger acid, carbonic acid. And that's going to release a proton into solution. So carbonic acid could go to a proton plus HCO3 minus, which is bicarbonate. Sodium bicarbonate would be what you find in baking soda, for example. But this proton that gets released by carbonic acid then will react with the hydroxide in the solution to form water. So we'll neutralize some of our hydroxide ion, OH minus, because the CO2 dissolves in the solution. So over time, the concentration of hydroxide, remember we use the brackets like this to determine concentration, this goes down over time. So what wineries should do is check the concentration of sodium hydroxide before they do a titratable acidity assay. But that often isn't done. Today we're going to do it. And here's how we're going to do it. We are going to take a known amount of a chemical called potassium hydrogen phthalate, or some chemists would call it potassium hydrogen phthalate, if you want to add the ph in there. So potassium hydrogen phthalate. The thing about potassium hydrogen phthalate is a weak acid, and it is also easily dried in an oven. So what drying does is it gets rid of all the water that might be attached to this molecule, makes it nice and dry. So when we measure potassium hydrogen phthalate, we know exactly how much we're getting. Therefore, we know exactly how many protons it will release. If we use this to neutralize NaOH, just like we used NaOH to neutralize acids in wine, let's add neutralize here. If we use this to neutralize NaOH, and if we know exactly how much NaOH is in, or exactly how much hydrogen phthalate we've used, then we'll know the concentration of our sodium hydroxide. So it works like this. We will go into lab and we will get a little weigh paper and we'll put some potassium hydrogen phthalate on there and we'll weigh it out. Then we'll throw that and we'll weigh it on an analytical balance, which are the very sensitive ones, as opposed to the top loading balance, which is a little less sensitive. So I'll show you those in class. We'll weigh it out on an analytical balance, and then we'll put that into a beaker, an Erlenmeyer flask probably, and then we'll titrate with our sodium hydroxide solution. And this is the solution we want to know the concentration of. We want to standardize our sodium hydroxide solution. And based on the amount of the volume of sodium hydroxide that we use, we can determine the concentration of sodium hydroxide. And the way that calculation works is like this. So potassium hydrogen phthalate has a molecular formula of C8H5O4K, or potassium. So let's get the molecular weight of that just for practice. We have to grab any periodic table, and so if you don't know offhand the molecular weights, we'd have 8 carbons, so it'd be 8, so the carbons would be 8 times molecular weight of carbon, which is 12.011. We looked at that in class earlier. We have 5 hydrogens, so 5 times 1.001, rounding its molecular weight, or atomic weight rather. And oxygen would be 4 times 16, and that's 16.00. And then potassium would be 1 times 39.01. All right, you can do the math on that, and it should work out to a formula weight of 204.44 grams. 204.44 would be the molecular weight, and 1 mole of that would be 204.44 grams. So I'll let you check that on your own. Okay, so we've got that. Now, what we need in addition is this. I'm going to erase this. What we need in addition is we need to know the stoichiometry of the reaction, the neutralization reaction, and it looks like this. Potassium hydrogen phthalate plus sodium hydroxide goes to C8H4O4 minus 2 plus potassium plus H2O plus sodium. Squeeze it in here on the far right side of the slide. Okay, so what's relevant to us is one of these hydrogens neutralizes the sodium hydroxide. So that half reaction would just be this. So what's the stoichiometry? For every 1 molecule of potassium hydrogen phthalate, 1 molecule of sodium hydroxide is neutralized. So the stoichiometry is 1 to 1. So that way, if we know that if we have a certain number of moles of potassium hydrogen phthalate, we're going to neutralize the same number of moles of sodium hydroxide. All right, so our moles of KHP, potassium hydrogen phthalate, are going to equal our moles of sodium hydroxide. Well, how do we get our moles of KHP? We weighed KHP on our analytical balance. So we have certain grams of KHP. To convert that to moles, we just use the conversion factor of 1 mole, figuring out which one goes numerator and denominator, divided by 204.44 grams of KHP. And that'll give us our moles of KHP, right? And this would be moles of KHP and we'd fill in the number of grams here based on our weight, and that would give us moles of KHP. And just checking, as we always should, to make sure our factors, our units rather, cancel. Grams of KHP in the numerator, grams of KHP in the denominator cancel, and we get moles of KHP. Okay, so we're good. So now we need to use that amount, that number, to figure out the concentration of sodium hydroxide. We know how many moles of sodium hydroxide were neutralized, so we know how many moles were in our sample. And so now all we need is the volume of sodium hydroxide from our burette. So just like normal, we take beginning and ending readings from our burette, and we get some kind of mils of sodium hydroxide, right? So this is from our burette. We have moles of NaOH, and we got that because it's equal to the moles of KHP that we originally weighed out and put in our beaker. So we neutralize all the KHP we put in the beaker, and that tells us the number of moles we needed of sodium hydroxide to neutralize that amount of KHP. So now all we do is just a simple division. We take moles of NaOH and we divide that by whatever mils of NaOH we use in the beaker, because we're looking for a concentration here. So we want the conservation in molar. Remember, we did molar, which is moles per liter. So we've got moles divided by milliliters here. All we need is a conversion factor. So we have 1,000 milliliters per liter. And our units are going to cancel, mils and mils. And that's going to give us some number for moles of NaOH per liter, which of course is just molar, right? That equals molar. And that's it. That's our concentration of NaOH, and we're good. And now we have an accurate number for our concentration of NaOH if we were to use that solution to do a titratable acidity assay. We would be very accurate in our determination of titratable acidity, because now we have very accurately determined our concentration of sodium hydroxide. That's what we're going to do in the lab today. We will talk later in the semester about an easier way to standardize sodium hydroxide using a density meter. But not everybody has a density meter, and it's good to learn the traditional way of standardizing NaOH. So that's what we are doing today. Thanks for listening, and I'll see you in class.